Good afternoon. My name's Matt Moore. I'm from Atlassian. I work in the build engineering team there with Pete Lachette, who spoke earlier this morning. But prior to joining the build engineering team, for the last couple of years I was actually leading the operations team, managing Atlassian On Demand, which is our software as a service platform. And today I'm going to be talking to you about continuous delivery. So quick show of hands, who knows what continuous delivery is? Alright. And who's actually got continuous delivery running in production? Cool, that's about what I expected. It's actually pretty difficult. So I'm going to talk a bit about our journey to continuous delivery. And I should probably preface the talk by saying that we're not there yet. So just quickly, for those of you that aren't familiar with it, continuous delivery basically is extending your continuous integration pipeline out to include acceptance testing and releasing of your software. Now, continuous delivery is different to continuous deployment in that continuous deployment you're automatically releasing to production. So as soon as your acceptance tests go green, your CI system goes, yep, sweet, going to deploy it to prod. In continuous delivery, you've got a human in the middle there pressing a button. And so I'm talking about continuous delivery, not continuous deployment. Cool. So this is our happy path. Atlassian, funnily enough, internally being a pretty large software company these days, I spend a lot of time talking about continuous delivery. And we've decided that we're going to man up and commit ourselves to some dates. And so by December 2014, we want to have a couple of releases going out every day to production. And so this is the curve that we need to hit. As you can see, we started out in 2011 there, releasing every 3 months, and more often than not, that ended in a fair amount of pain. And then as we matured, we got to fortnightly releases and then weekly releases. So Atlassian On Demand was launched to the public in October 2011 after a couple of years of development internally. It actually runs the same software that you can download to run behind the firewall from Atlassian's website. And the way that we do that is by running a very, very small virtual machine per customer. And that means that we have a lot, and I mean a lot, of virtual machines. So as you can see here, when we launched in October 2011, we had about 500 beta testers on the platform. As we hit January 2013, we had about 24,000. And as of last month, we cleared 40,000. So 40,000 virtual machines, that's a lot of places to be releasing software to. Atlassian applications typically look something like this. Take it with a grain of salt, I'm not a developer. But basically, it's roughly the same as most other large applications. So you've got the core of the application, which provides some basic APIs, some bundled plugins that do fundamental parts of the application, like providing a REST API, search, browsing, that sort of stuff. And then we've got sort of an open slather plugin area where either other teams inside of Atlassian can provide plugins. So we've built things like Service Desk on top of Jira as a plugin, or external vendors can write plugins against our APIs and ship them to run inside of our products, inside the same JVM. So it's pretty straightforward. We'll come back to that in a minute. What that's allowed is many developers, or many teams of developers, to be working on different parts of functionality at the same time, in theory without stepping on each other's toes. In practice, it mostly works, as you find with any large software development project. The way that everything gets bundled together is using Maven, pretty much the standard for Java projects these days. And Maven has this horrible file called a POM file, which is a really, really large chunk of XML, which specifies all the dependencies, all the components of your application. And What happens when you do a build is that Maven goes through, sources all those dependencies, builds them as necessary, and then compiles them all up into one file, usually a war file, which is basically a tarball. But in on-demand, we actually ship a suite of applications. So we're shipping Jira, Confluence, Bamboo, Crowd, and all of those applications talk to each other. And they talk to each other typically through REST APIs to do things like issue creation from Confluence into Jira, provide a common header bar, do cross-product search, that sort of stuff. And the issue that we had as we were launching this platform was that we weren't really sure how to specify, yeah, Confluence 5.1 totally works with Jira 6. No, it's not going to be a problem. Or Confluence 3.4, Jira 6, maybe not so much. So as we were looking at this problem, we went back to thinking about the way that we bundled up our applications, and Maven thought, well, you know, roughly analogous. So enter the fireball. We built this giant Maven artifact called the fireball, which takes all of our applications, all of their bundled dependencies, and all of the third-party plugins that we wanted to ship in the suite. And it's a couple thousand lines long, and it builds this mecha artifact. It's 600 megabyte tarball that we ship out to on-demand. And it's a pretty interesting build process because Maven goes through and looks for all of the dependencies. So it's got it set up with a manual build at the moment. So when the product teams say, yep, we're good for release, one of the developer who's on the fireball or on release that week goes and clicks the green button, and about 6 hours later, this tarball spits out the other end. As you can imagine, Atlassian not really short on build infrastructure. It's a pretty intensive process. The fireball itself actually gets deployed into an OpenVZ container. So each customer gets their own VM, as I mentioned earlier. That's an OpenVZ container. All of their applications run within the container. And the whole container itself is backed onto an NFS file system. Supporting the applications, you've got Postgres for database and Apache for request routing. We run many containers on each compute node, and we run many compute nodes per rack, and we run many racks in a data center. That's how we achieve the scale. And again, going back to my earlier point, that's a lot of things to be deploying software to. The way that the firewall gets installed is pretty interesting. There's a shell script written by some developer who existed or at some point along the way. I think he left the organization by the time that I joined, almost 3 years ago now. And it does a whole bunch of things, but the crux of it basically is it gets a list of install services and then iterates through the install scripts for each of those services. So, you know, stuff happens, and then at the end of it, you either get a thumbs up, everything's good, or it explodes in your face. Right? That's the way shell scripts work. Surely you know that's going to happen. As it turns out, the way that these shell scripts run, the way that they interact with each other is not very deterministic. So it's actually really hard to tell, even if the shell scripts have completed and given the right exit codes, whether the upgrade process has succeeded or not. Things like the way that the applications start up, and this is pretty standard for Tomcat Java applications, is asynchronous. So they sort of sit there and spin in the background after you kick off the process, demonize and do stuff for a while before they come up. Part of what we do there is loading all those plugins that we get from our marketplace vendors and other teams within Atlassian. Other things we do are upgrade tasks, so it might be doing complex data transformation on startup there. So it could actually take quite a while before your service comes up. You're not really sure what the story is there. So digging into this was a really interesting few weeks of my life that I probably would have rather foregone. As it turns out, all these install scripts basically depend on each other. So when you install Jira, it depends on Postgres and Crowd. Crowd depends on Postgres. Confluence depends on Jira, Crowd, and Postgres. So what happens when we need to do something like change the collation in Postgres? So we need to change the character set that Postgres uses to generate things like indexes. It gets really interesting. You get all sorts of very strange side effects, and usually the world blows up. Weird things start happening, like we deploy this in production on one rack, and new instances started getting provisioned with half a Bamboo database. And what was happening was that Postgres was restarting and trying to change its collation in the middle of Bamboo, trying to load its initial data set. So modification, not very easy. It's very difficult to reason about. In addition to that, in addition to the obvious blowups in your face, there's all sorts of unexploded bombs lying around. So sometimes, a couple of days or a week after the fact, you come across an instance that, or our audit scripts would pick up a failure in the upgrade process, and we have to then very carefully go in and rectify that customer's instance, and usually come up with some crazy script to run across the infrastructure to make sure it didn't happen again. Not a very happy place. That said, you do what good ops engineers do, you do what good service providers do, and you roll for it. And you keep rolling. And so we managed to actually get this thing to weekly releases at this point, which was a fairly sizable achievement, I think, given what we're dealing with. So we rolled on from there, and we're sort of looking at this graph here. And we're sort of considering this line here between weekly and daily releases. And the way the platform's structured with a VM per customer is we do high availability at the VM level. So if your VM goes down, it'll restart somewhere else, and you'll keep on rolling. But we don't do it at the application level. So any upgrade that we do to the core application is downtime for a customer. And we didn't think that, probably rightly so, that the customers would be very happy with their application going down, once or twice or 3 or 5 times a day as we upgrade these things. And obviously rewriting the whole application with each of the applications, there are 4 of them, to take this into account wasn't really going to happen in the time frame that was available. So we started looking deeper, and we came back to this. So the plugin system that we talked about a little bit earlier. And as it turns out, plugins depend on OSGI, which I don't know if any of you have had the interesting challenge of wrangling, but it's a pretty special framework. But it does allow you to dynamically unload, reload, and load plugins. So we can, in fact, do upgrades on the fly of plugins within any Atlassian application. So that was pretty cool. That's a really great way that we can get from that weekly release to the daily release. So taking into account all these problems, we sort of looked at the firewall and cringed a little bit, and we decided to come up with the total opposite of the firewall. So some bright spark came up with the name icebat, opposite of firewall. Fair enough. icebat doesn't actually have a logo, so well. And the icebat is actually a series of Puppet manifests. And what this allowed us to do was to decompose the problem into a way that we could reason about it much more effectively. So we generalized the installation and configuration of the applications. At the end of the day, you're just configuring a JVM and Tomcat, plus a few special parameters per application, into a single module, which we then use shim modules that do the minor specialization for each application to call. And there's a single dependency in from each application to Postgres. So you have a nice, clean dependency graph It's really easy to reason about making that change. Same deal with the Apache module. Each application injects its request routing configuration into Apache, and off we go. No more dependency help. We also wrote a really neat little defined type to handle Atlassian plugins or OSGI plugins. And so we can now install these plugins into applications independently, have them versioned, properly maintained by the Puppet manifests, and so on and so forth. So when it came to doing the Postgres change under this new model with the icebat, everything was a lot easier because we knew that we could make the configuration change to Postgres, that Puppet would order the dependencies right and would produce a nice clean graph, and that Postgres would get restarted once and then everything else would sort of cascade off it. Win. The other thing that the icebat got us is that we started thinking about this problem of, how do we get stuff into production really quickly? And one of the issues with this mess of shell scripts that we had previously was that change was really hard to reason about, to implement, to test. And so we started thinking about it a bit more, and we realized that what we actually wanted was to treat the versions of our applications as data. We wanted to be able to split those out, have Joe Random Developer specify, yep, I want version 5.4 of Confluence, 6.1 of Jira, off we go to the races. And by doing that, it meant that we have quite a low rate of change in the actual Puppet modules themselves, and a high level of visibility into which versions are getting deployed here. So we've effectively replaced this giant XML file in Maven with a really tiny versions.yaml file, specifying which versions of the applications work with each other. The other thing that this got us was the ability to specify different environments. I mean, Hira being structured as it is, it was really easy to then go, right, well, we want this version.yaml for this, for development. We want this version.yaml for dogfooding, so our staging or testing environment. And we want this one in production. And then we can promote between the three. Very, very straightforward, very easy to deal with. Most importantly, really, really easy to reason about. We also got local overrides. So not every instance is created the same. Some customers might have 1,000 users and 100,000 issues on there. Others might have 2 users and 10 issues. The reason that local configuration is important is to try and work around those edge cases so that we can extract the commonality between them. So by implementing a hierarchy where we have global configuration, data center local, rack local, and local, means that not only can we work around those edge case customers, we can also try new ideas on the rack level. So Canary, new deployments. So if we're rolling out a replacement for Crowd, which is something that we did last year, we rolled that out on a couple of racks. Then we rolled around at a data center level, and then we rolled it out globally. And that gave us a really high confidence in that change going out to production and not waking me up at 3 a.m. Unfortunately, the side effect of this was that Jason, who actually did the hard yards and wrote these Puppet manifests, ended up spending the vast majority of his time as a mechanical Turk, updating versions.yaml and checking that into the Git repo. This obviously wasn't a very sustainable strategy. I don't know about you guys, but I don't really want to pay someone a senior developer's salary and have them editing YAML files all day. I don't think it's a very effective use of his time. I would much prefer that he gets back to shooting things with arrows. So we tossed it around for a while and we introduced a new tool, which effectively is an external backend to Hira. We call it Manifesto. Manifesto has this beautiful dashboard, as you can see here, that gives you each application, the plugins that go into that application but are outside the core application itself, so they're not in that bundle plugins directory. So whether they're vendor supplied or again developed internally. The environments that things are being deployed to, and which versions are in each environment. Really straightforward, really easy. And the way it works is that we have a client, and use the term pretty loosely. It's basically just a Python script. It hits factor on the local machine, so each customer instance. Looks up the environment it's in, whether it's dog food or production. Looks up which products are licensed. And then formulates a request to the Manifesto REST API. And the Manifesto REST API returns a higher, I don't know whether you call it a manifest or just a set of higher facts. And the client then calls pub apply with that higher manifest in place, again referencing the factor variables. It's all pretty neat, pretty clean. And because of the way that we've structured Hire with that global data center rack and local changes, it means that the majority of manifests are the same. So what we do is we basically just generate one manifest on the Manifesto server for each combination of client environment and so on and so forth, and then we cache it. And so off we go. It's very quick, very scalable. Awesome. So we're now at many deployments a week. Just jump back to this one for a sec. So the other thing that Manifesto gave us is self-service for developers. So developers can actually come out and say, right, I want to promote version 0.7 of Atlassian Health Check into Bamboo there. I want to stick that in dog food. I'm committing to the fact that this is past development, and then after it's been in dog food for a while, it's going to go out to production. And developers get self-service, again eliminating that mechanical Turk in the middle there, and getting us much closer to to getting from many releases a week with the plugins to twice daily to hopefully in a few months, 18 months, many per day. Cool. So next steps for us are to get all of the products and all of the associated plugins into Manifesto. So that development teams can control their own destinies. We want them to be able to do releases to production without bothering the operations teams. But to do that, we also need them to instill in us a high degree of confidence in their automated acceptance testing. So make sure that they're not going to break that contract between the different applications in the suite, and make sure they're not going to do anything untoward with customer data. We're going to introduce fault tolerance for Manifesto, and we're going to get rid of flywheel. We may also introduce controls for feature flags, which we're starting to use pretty heavily within the applications. Special thanks go out to Ryan Thomas and Jason Birch, who I don't think are here today, but those guys actually did the heavy lifting on getting Manifesto and icebat out the door. I was involved in the conception, but not a huge amount after that. All right. And that's that. Thank you very much.
Thanks, Matt. Any questions for Matt? Hand up.
Yep.
Oh.
Okay, so you said you have pretty much unlimited compute resources. Great. That's not true. How do you manage to control your devs deploying stupid amounts of compute resource?
So what do you mean exactly by compute resource?
Okay, instances. How do you keep
Oh, right.
from deploying unlimited numbers of instances and just leaving them lying
That's a pretty interesting problem. In general, we trust our developers. So devs can't actually create production instances themselves. So customers can do that when they sign up for the website.
Those two sentences don't align.
Wait for it. Wait for it, Jeff. So the development and dog fooding environments, they can create all the instances they like. We have finite compute capacity in each of those environments. We maintain a whitelist of instances that are required for things like QA, exploratory QA, continuous deployment processes and that sort of stuff. We ensure that those instances are always on and available. Everything else gets regularly killed. Does that answer your question? Cool. Anyone else?
Any other questions? Okay, I'm running. Hold on.
How's your experience with OSGI containers and auto code loaded and unloaded?
It's pretty interesting. We've found a whole lot of bugs in Tomcat along the way, and in our own code. The biggest ones that have hurt us have been the way that Tomcat keeps references to unloaded plugins around after you unload the plugin, which is it's a pretty severe drain on your permgen and heap, which are obviously one and the same in Java 7. But memory is the most critical scaling resource for us in the Unicorn environment, so the SaaS environment. So constraining that as much as we can is really, really important.
So just a question around what tools you're using, interestingly enough. Because we basically followed Atlassian's lead on Bamboo being a centerfold universe. Do you use that for this particular solution?
So we don't use Bamboo to do the deployments. We use Bamboo as the CI. So if you think of it sort of as the 8-armed monster in the middle doing the job control. So all of your task execution and that sort of stuff. And we have Bamboo plugins that then talk to another tool that we've got internally called Deployment Engine, which knows in great detail about the structure of the Unicorn environment and at what rate we can execute these upgrade tasks. And that in turn sort of hooks into Manifesto. Scaling. We looked at it and we looked at actually building Deployment Engine into Bamboo. We decided that wasn't really sensible for either us or our customers. I mean, the way that Deployment Engine operates and the knowledge that it has of the Unicorn environment doesn't really make sense for anyone outside Atlassian. And I haven't yet encountered anyone that's got 40,000 VMs they need to upgrade in parallel. So, okay, we can talk afterwards about that.
Any final questions? Thanks, Matt, and thank you to the team at Atlassian. Great presentation.